Hi everyone. I hope the audio and video quality is good. Maybe we can get started. In today's session, we'll focus more on random forest algorithm. It's covered in lesson 6 of Fast AI, and especially in random forest, we'll be covering lots of pre-processing techniques and models with decision tree and random forest, and what are the hyperparameters we can tune with both decision tree and random forest. And then we will learn a few techniques to interpret the models. So we'll be doing two different data sets. One is Titanic dataset. For Titanic dataset, we'll be using Kaggle. And then for another dataset is Bulldozer dataset. For Bulldozer dataset, we'll be using Google Colab. I will show you how to move data from Kaggle to Google Colab using Kaggle API. Yeah, we can get started with that. I'll share this notebook with you all, maybe after the end of the session, or you can find this in course.fastai. If you go to lesson 6, you can see this lesson is based on chapter 9 and then how random forests really work. So there are two notebooks. So when you click copy and edit, for me it's showing edit my copy because I have already created a copy. But for you it will show like edit and copy, something like that. You can click that. Once you click, it opens a Jupyter notebook. Here you can run code. So let's start with this dataset, Titanic dataset. So this Titanic dataset has a few columns. I'll show you, and we are going to predict whether someone is survived or not. So this is a binary classification model. So let me show you the data. Cool. So you can see it has few columns like passenger ID, survived, P class, name, sex, age, and few others. And we are going to predict whether someone is survived or not. This column, this is the one we are interested in. So this is a binary classification. And let's quickly check its distribution. DF survived dot value counts, and you can see 342 people survived and 549 people not survived. If you add normalize equal to true, you can see a percentage. So 61% of the people not survived and 38% of the people are survived. So if I give you some data like this, we are going to predict whether this data is survived or not. So that's the goal of this project. So while doing so, we will understand how decision tree and random forest works. So first of all, we'll be doing some pre-processing. So random forest and decision tree, they require very minimal pre-processing steps. One is if something is missing, we can convert that to filling some values. Here, Jeremy used 0, but you can also fill using mean or median. It depends on the context of the column. Generally, 0 should be fine in this case. And then this log far, if you see the original distribution of log df far, so it looks like strange big numbers. So if you see this, most of the fare is like less than 100, and if you see some values are really big, and then to convert that, Jeremy used log fare, taking log of this number. So let's plot that. So this is the distribution after taking log. Cool, this looks good. And then if there is any categorical features, we are converting that to pandas categorical. And even you can pass some order. For example, let's say there is a column about education. It's like 10th standard, 12th, then first year, second year, third year, and fourth year, then masters and PhD. In that case, instead of randomly allocating some number, you can create an order like 0 to 10 based on the education levels. Cool. So for this dataset, we are using only a few columns because some columns doesn't make a lot of sense. For example, name and other things like ticket. We can extract some features from here, but to keep it simple, we are taking only very few features. For categorical features, we are taking sex and MPOCT, and for continuous features, we are taking age, SIPS, SP, and parents and children. I think this is about siblings, and this is about parent and children, and log fare and P class. And this is our dependent variable. This is the one we are trying to predict survived. So you can see this is the original data. Sex is male and female. After converting this to categorical, you can access the code using .cat.codes. You can see the real representation of these things. Cool. Now we are going to see about 1-hour model. So decision tree. Before starting decision tree, let's talk about a little bit on this one. So this chart shows what model to choose based on the problem. Let's say you are starting here, and if the sample size is greater than 50,000, if you are going to predict a category, you are going to go here. If it's labeled data, you can go here. And if the labeled sample is less than 100,000 data points, you can do these things. And if it's like no, you can go here. So it's all about taking decisions. We take lots of decisions every day based on lots of information. So how decision tree work is, it's very similar to this. You will start somewhere, and then you will try to split the data into many groups, and then finally you will reach some bucket, and you take the average of the bucket. If you take an average of the bucket, that's called regression. And if you are taking mode of the bucket, which is what is maximum in the bucket, that's classification. So if you remember 20 question problem, let's say you are trying to think about any person, and I will ask you like less than 20 questions, and I will find the person. So it's like the first question should be like whether the person is male or female. So if I ask male or female, I can divide the data into two large groups, two equally splitted groups. Then I can ask whether that person is alive or not. If it's alive, I can further split the data into two groups. Then based on your answer, if you say let's say the person is alive, I can ask other questions like whether that person is lives in Asia or China or India. So if that's the question, I can equally divide the data into very good proportion. Then further, I ask a lot of questions, less than 20 questions, I can predict the person. So the same concept applies in random forest. So we'll try to find a split, a perfect split at the beginning. So this is the distribution of survival rate of sex. If you see this, a lot of female, they are survived, and male is only very few males survived. So if you take sex as a feature, so you are very good at predicting some of the survival rate. If it's for numerical features, you can take a numerical feature and then you can, for each value like 2.7 or 3.6, and then you can further divide the data into two groups, and you can take an average of how many people survived in each bucket. So here you can choose any feature. For example, let's say I'm taking age, and then if the age is like 10, currently it's not moving much. Oh, I need to rerun a few things. Let me run from here. Okay, maybe I'll run everything from top to bottom, and then I'll go to the top and explain things. Cool. So let's go to the top. So here what we are doing is we are splitting the data into two parts, training and testing. So we are taking 75% for training and 25% for testing. Then we are, for categorical features, we are converting that to the codes. We already did that in the pre-processing step. So after running this, everything became a numerical value. I'll try to show you train df. You'll see it looks like this, but if I take some of the features, let's talk about sex. So initially sex is like male or female. Now it becomes a number. So you can ignore the other columns. We'll be considering only categorical cats and then continuous columns. We have already listed those here, categorical features and continuous features. So we'll be using only these features. So here we are trying to use sex as a feature. If sex equal to 0, which means I think female is coded as 0, our predictions will be, if it's female, we are going to predict they are going to survive. If we use this approach, our model will like close to 79% accurate. So this is like mean absolute error. This is error, but if we consider the accuracy, it's like 1 minus the error. So it's like 79% accurate. So if you say, if someone is female and we are going to say they are going to survive, then our model is like 79% accurate. So that's a very powerful feature, right? We are taking only one feature and then we are going to predict whether something going to happen. So this is called one OR model, which means only one rule model. So our rule is, if it's female, we are going to say they are going to survive. So this is just only one rule. This is called one OR model. So here we are using continuous feature. So this is like survived 0 and 1, and you can check their fare. For people who survived, their fare is a little bit higher than this number, median. So we can say if the fare is greater than 2.7, we can say that person is survived. So if we use this rule, our model will be like 33% error. In other ways, it's like 67% accurate. So this is quite a bit less accurate than our previous model, sex as a single binary split. So here we are creating a function score and site score. So what's going on here is, let's say we are taking some column, and then this is the one we are trying to predict. And if we use some value, then we will see how good the prediction is. For log fare, this number is 0.47, and for sex, this number is 0.40. So this is impurity score. I will explain impurity score when we see some decision tree splits. So I will explain Gini when we see this. So let's continue. So when the Gini is less means that's a very good split. So here what we can do is we can choose a feature and then adjust the value and see what happens to the Gini. So if some feature is continuous, we can experiment with all the individual values in this column and then choose the one based on the Gini. In this case, when score is, the position is 6, we are getting very good score. For age, I think the way, if you split the data by age greater than or equal to 6, we will get the Gini as 0.47. That's the best score for age column. Likewise, we are finding what's the perfect split for each column. For sex, if you use greater than or equal to this number, female is the perfect split. For MPOCT, 0 is the perfect split. And for age 6, similarly for other features, you can see the number. So here we are going to create a decision tree. So far what we have learned is finding only one split. This is called one OR model. So we can find one split based on the Gini. Then what can we do better from one rule? We can add more rules. For example, we already know that sex is like a perfect feature. If we use sex, our model is like 79% accurate. So let's say we are using sex, we'll get 2 more tree, right? Whether the person is male or female. If it's male, we can try to find one more split, one more rule for male, and also we can find one more rule for female. So if you do that, what happens is we are creating 2 rules. So this is called 2-OR model. So here what we have done is we try to find males data and females data. For male data, we are trying to find what split we can use. We passed all the columns other than sex. So if you remove sex and if you pass other features, you can see for MPOCT, the Gini is 0.387, and you can see the values. And also for female, you can see the Gini value. You will pick the lowest Gini number. In this case, age is a perfect number for males, and for female, I think the perfect is P class. Yeah. we can see the best next binary split for males is age less than or equal to 6, and for females p class less than or equal to, this is the perfect split. And then we will continue this with many rules. So this is decision tree. So here instead of programming ourselves, we are going to use scikit-learn decision tree classifier. And in the decision tree classifier, we are asking max leaf nodes is 4. Once the max leaf node is 4, we will stop the tree. So we can go through this. So if you see the first one, sex less than or equal to 0.5, in this case, our sample is split into 2. This is female. So number of female in the data is 415 in the training data, and 253 as female. Sorry, male, and this is female. If you see this, if both are equal means you will get a number close to 0.5. And if one class is very high means compared to the other class, other one, it's like, let's say this one. If you see this one, it's like a perfect split, right? So most of the people here are male and only very few female. In this case, the Gini is 0.06. So this is like a very good split. So when the numbers are here, if the numbers are equal means you will get the Gini as close to 0.5. Yeah, this is like a good example. You can see the values are equal. Male in the data and female in the data are very equal. So in that case, the Gini is 0.5. And if for the perfect split like this, you'll get the lower Gini. So our goal is to find the lower Gini. So you can see how Gini is calculated. So here we are constructing a decision tree classifier with min samples leaf as 50. So when minimum samples in the tree is 50, we can stop. If it's lower than 50, we won't go until lower than 50. So 50 is like our maximum number. You can see number of samples is always greater than or equal to 50. So here what we are doing is we are starting with sex, and then based on the sex we are going either direction. Then if we go to the bottom leaf, here the sample is only 50. If it's 50, we will stop there. We won't further split. In this case, we reached 50, so we won't further split. But for in other area like here, the samples is 265, so we split. Likewise, you can split. So when sample is 50, we stop. Now let's talk about random forest. So if you see random forest, there are two words, random and forest. Forest means a collection of trees. So instead of one tree, we can use many number of trees. So if all the trees are same means it's not helpful. So what we are going to do is we are going to add randomness to the trees. So how can we add randomness is there are two ways to add randomness. For example, in each tree, we can select only some sample of the tree, randomly selecting some samples. Let's say you have got 100 data points. In the first tree, you will select randomly 80 data point. In the second tree, you will randomly select another 80 data point. Likewise, you will create many trees. So that's one way of random. And another way of randomness is introducing using the columns. Let's say you have got 10 columns. In the first tree, you will randomly select 7 columns. In the second tree, you will randomly select 7 columns like that. So we are introducing some randomness. So the concept here is, we can read this. The idea is that we want each model's predictions in the average ensemble to be uncorrelated with each other model. So if all the tree are random means, selecting different rows and different columns, then the errors should not be correlated. They are like uncorrelated. That way, if we average the predictions, the average will be equal to the true target value. That's because the average of lots of uncorrelated random errors is 0. So that's quite an amazing insight. So here, what we are doing here is get tree. So in this tree, let's say we have got some training data length, and we are taking only 75% of the sample in the data. So when you run this many times, each time you will get a random 75% of the data. So here we are creating many trees. In each tree, the columns are completely, the data sample is completely random. Then how do you make a final prediction is you take an average of predictions in each tree. In this case, our accuracy will be like, the error is 22% if you do 100 trees. Also, we can implement random forest using scikit-learn random forest classifier. Here we are asking to create 100 trees, and minimum samples leaf in each tree should be 5. And we are fitting the tree. And if you do 100 trees with minimum samples leaf equal to 5 means we are going very deep. So if you see this this one, minimum sample leaf is 50. If it's 50, we are stopping here. But 5 means we will go further. So our tree will be very deep. But each tree, if it's like very deep, and if we take an average, the errors will cancel out, and we are getting like a very good model compared to single decision trees. You can see it here. So that's the concept of a random forest. So once a random forest is created, or any decision tree based model is created, we can find what are the important features in the column, in the data. There are many ways to find feature importance. Maybe I can quickly explain 2 ways. One way is using the Gini index. So if I use 6, the Gini is like 0.47. And then if I use another one, logfar, the Gini is reduced here. And if we use another feature, you can see the Gini is reduced. Likewise, I will see how many times we are using sex as a feature, and then we will see the Gini improvement. We can use that to calculate the feature important. So that's one way. And another way is once the model is built, for each column, we randomly shuffle all the rows in that particular column, and then we try to make some predictions. If the prediction is worse means, then that feature is very important, because if we randomly shuffle that, our predictions are getting worse. So we can consider that as an important column. So those are 2 ways to find feature importance. And there are better ways nowadays, especially with SHAP. So it's here. So this is a way to find feature importance. So you can read this paper. So you can see this library. So let's go to the lessons. Okay. I think we are pretty much done with this notebook. Let's move to the other notebook. So in this notebook, we are trying to predict the price of the bulldozer. Before going here, let me show you the data. Maybe let me search. This is Blue Book for bulldozers. So this is the data set we are going to use. I will quickly show you how to get data from Kaggle to Google Colab. So this is the data set we are going to use. Let's see the data. And the data has train, valid, test. And then the key fields are sales ID, mission ID, sale price, sale date. And there are also a few other columns. I think there are around 50 columns. Cool. So the first step is you need to so let's say you are in this page for the first time. When you click data, it will pop up a agree to download. So you need to accept that. Otherwise, you cannot download the data even if you are using API. So that's important. So you need to agree and download. Once that's done, so this is the data we are going to download. So you need to keep a note on this name, Blue Book for bulldozers. So we need this name to download the data using API. So that's step one. Step one is agree and agree for download. Then go to, let's go here. Okay. Go to your profile. Sorry, I think account. Okay. Go to account. And you can see API using Kaggle's beta API. Create new token, API token. If you click this, it will download a JSON file. In that JSON file, if you open the JSON file, you will find two things. One is your username, and other thing is you will find some key. Keep a note on both. I will share this notebook end of the session. I think I copied most of the things from lesson 9 of the notebook. Lesson 9 of Fast book. Cool. Okay, so if you open the JSON file from Kaggle, you can see your username and key. You can replace this xxx with your username and this with key. Then you can run this. Then here we are saving the JSON as kaggle.json inside our computer. Cool. So once that's done, you can enter the competition name. So if you go to the Kaggle, I think it's here. So you should keep a note on this one, Blue Book for bulldozers. This is the competition name. So here you can enter the competition name, and then we are setting that as a path. Then we are using Kaggle from Kaggle input API, and then we are going to download the competition in this path. And once the download is done, we are going to unzip the data, and you can see it's been downloaded, and you can see some of the files inside the downloaded folders. So for our project here, we are going to use train and validate CSV, and this has around 50, I think more than 50 columns. Oh, 65 columns. And if you see this, there is a date, sale date. So there is a column called sale date. So we'll be doing some feature engineering. So generally, if you see, maybe let me show you the data values. Okay. So you can see it has a lot of numerical features and categorical features, and then lots of missing values. And also there are some Boolean features. Cool. I think the Boolean features comes from our feature engineering because I have already, maybe let me rerun this. Okay, so originally there are 53 features. I'll show you those 53 features. Yeah, you can see it here. So mostly numerical features, categorical features, and then lots of missing values. Yeah. So if you see those features, there is a column called date. The date column looks like this. You can see it here. It has day, month, and year, and some timestamp. And here you can see some categorical feature, product size. So this product size has medium, small, large, medium, mini, large, compact, and we can arrange in some particular order: large, large, medium, medium, small, mini, compact. So we are arranging by top to bottom, highest to lowest. Then we are converting that to category, and then once the category is done, we are setting the category as in some order. So if you see this, in mostly for random forest and tree-based models, we'll be doing only very few minimal data pre-processing steps. One is converting everything to categoricals. We no need to do one-hot encoding because if you just convert everything to categorical, the column becomes a number. Then our tree will ask lots of questions, and then it will find the correct column that's needed for a perfect split. So we no need to convert everything to one-hot encoding. We can still use normal numbers like 0 to some length of the categorical columns. So that's one pre-processing step. And the second is filling missing values. So filling missing values, you can use median, mean, or 0 or previous number. It depends on the domain. Cool. And if you see this, there is a column called date. So from this date, we cannot directly use this date as it is. But what we can do is we can extract many information from this date. So we'll see how to do that. So this is the column we are trying to predict. So if you see the original ones, let me show you. So it looks like this. So most of the price is like less than 80,000, something like that. But there are very few greater than 100,000. So we are applying log scale so that everything becomes compact range, 8.5 to 12. So this is a function from Fastai. So if you use add date part, you can pass a data frame and you can say what is the date column. It will create many features from this date. So earlier I showed you how sale date looks like. Now we are extracting many features from sale date. So you can see it here. So we have extracted sale year, sale month, week, sale day, and many more. So we are doing the same for test dataset. So these are the features we have created: sale year to sale elapsed. So there are quite a few features. Then, as I said before, the main important pre-processing steps are converting categorical features, and then if there is something missing, I will fill the missing values. So here we are doing some split. So our training data is sale year less than or equal to 2011, and then sale month less than 10. If that's the case, that's our training data, and remaining things are our validation data set. Fastai blog has a very good blog post on how to create your validation dataset. I highly recommend reading that. Cool. And there is a function, continuous categorical split. Here, if you pass a data frame and your dependent variable, you can find what are the continuous features and what are the categorical features. It's quite useful. So there are lots of categorical features in this dataset. I think we have seen this in the last session. So we are quickly creating tabular pandas data frame. So we have created a dataset for training. So XS is our input data and Y is our prediction. And you can see this is our validation and validation predictions. We are creating a decision tree with max leaf node as 4. So we will max leaf node as 4. In this case, we'll stop at 4. So once we reach 4 leaf node, we'll stop. So that's the condition. So this is one decision tree. And since we are trying to predict the price, this is a regression problem, and we are going to use mean square error and root mean square error as our metric to optimize. So for a perfect model, you will reach root mean square error as 0. So when the tree is very deep means it's going to here we have not set any parameter, hyperparameter. In that case, our tree will be very deep. If the tree is very deep means it's going to learn each individual data point. That's why the mean square error for the training data is 0. But if you check the same for validation data, it's quite high, like 33%. I mean 0.33. Then here we are creating a random forest model. Our default hyperparameters are number of estimators equal to 40, which means we are creating 40 different trees. And in each tree, we are selecting only 200,000 data points. And then maximum features is 0.5. Let's say we have got 65 features. In each tree, we will randomly select 50% of the features. Then min samples leaf is 5. If the minimum sample leaves equal to 5, we'll stop, otherwise we'll continue. So each tree will be like very deep, and we have created like 40 different trees. Once that model is done, you can see this is your training root mean square error, and here you can see validation root mean square error. So these are some of the predictions of the tree. So each tree will predict a different number, and this is like each tree. If you see this, you will see like 40 different predictions, and finally you can take an average of each prediction. For this row, you will take an average like mean 0. So each tree is predicting something. Like here, the first tree says for first data point it's 10.18, the second tree says 9.7, 9.2, and then if you take an average of everything, it should be like close to the truth. So that's the power of random forest models. And here you can see whether adding more tree helpful or not. So when we are adding only one tree, our root mean square error is quite high, close to 0.32. So one tree means that's a decision tree. Then after 10 trees, the increment in improvement of root mean square error is quite low. So you can see the trend. So here we are trying to make some predictions. Once the prediction is done, we are going to do some interpretation. So as you can see here, there are few things we can do to interpret the model. One is how confident we are with our predictions. So that's one thing. The second thing is what are the important features in this model. That's other thing. Then partial dependence plot. I will explain when we go to that section. Then tree interpretation. It's like interpreting each row, why we are making some prediction. So that's quite powerful. So the first one is prediction confidence. So let's say we are going to make some prediction, how confident we are in our predictions. Let's say if all the trees says almost similar number, then we can say that's a very good, we can trust that prediction. So the confidence should be high. So we can find that, we can use standard deviation to find whether that prediction is quite confident or not. So when standard deviation is low means there is not lot of change in the prediction. In that case, the prediction is quite confident. If the standard deviation is really high means each tree is saying different number, so we cannot trust that prediction. So we can assign some low confidence for high standard deviations. If you see this, for the first tree, the standard deviation is 0.25, quite high compared to the third prediction. If you see the third prediction, I think all the trees are very similar predictions, so we can trust the prediction. So here we are plotting the feature importance. If you see this in this problem, the main features are year made, because we are trying to find bulldozer sale price. So for any vehicle, car, motorbike, the year made should be one of the top predictors. For example, if the year made is very recent, means you will pay more. If it's very old car, means you will pay less. So the same concept applies. The second feature important is product size. Then there are few more. So this is the same plot for feature importance. You can see year made is quite high, and there are few features, they are very less. So to make our model easy to deploy and maintain, we can remove lots of these low helpful features, because they are not contributing a lot. We can remove those and see whether our prediction accuracy improved or not. So here what we are doing is we are keeping only a feature greater than 0.005. So out of 63 features, only 21 features has greater than 0.005. So we are going to keep only those, and then we are going to build other models. So this model numbers are very similar to what we have seen in the past. So this is original columns, and this is our important columns, which is 21. And you can see the same feature importance, it's almost similar. Then there is other way to reduce columns. For example, this is a dendrogram. If you see this, how to read this is, you can see different colors, and you can also see something like this. If the distance here is very close to this axis, which means those two are same feature, almost the same. For example, tire size. Let's compare tire size with a sale year. So tire size, it's here and it's joining only very long distance. So we can say those two are very different feature. But if you see some features like sale year, sale elapsed, they are joining very close, which means they are almost very similar features. You can also see these three groups are very similar, and product group descriptions, they are also very similar. And base model and this one, they are also very similar. So what we can do is, if those two features are similar, means instead of using both, we can use only one to represent the same thing. So that's what we are doing here. So maybe before going there, let me explain this concept, get OOB, out of back sample. So what does it mean is, let's say, maybe let me write this. Okay, so we are going to learn OOB. So yeah, OOB square, you can see it here. So this is quite useful. How to, let me explain this. Let's say you have got 100 data points, and let's say you are building 10 different trees. So in tree 1, you are randomly selecting 80 data points. Then tree 2, you are randomly selecting 80. And in tree 3, you are randomly selecting 80. Likewise, you will select up to 10 trees, 80. So in each tree, we are not using 20 data points. So what can we do with those 20 data points is, let's say you are building some model. Once the model is ready, we can use the remaining 20 data points to test how well the model is performing. So this is called out of back sample error. So instead of using validation data, we can also use this data as a metric to check how good your model is. So if we use all the columns, our out of back sample error is 0.87. And here sale, if we use sale year, we will get 0.877. And if you use sale elapsed, you are getting 0.872. Here the lower number is better, so you will keep sale elapsed. So you will delete sale year. So that's why sale year is added to drop. So likewise, you can find what are the things to remove. Once that's done, you can remove those features. Then you are making some prediction, which is quite good. So this number is almost similar to, it's better than previous ones actually. Good. So once the model is done, we are saving the model as a pickle file. Okay, so here another important concept is partial dependence. So what does it mean is, once the model is done, let's say you are trying to find the importance of a single column year made. What is the true relationship between year made and your model predictions? In that case, what we will be doing is for each data, we are changing the year made to a single number. Let's say, okay, let me explain this. Let's say the year made ranges from, let's assume 1950 to 2000, something like that. So let's say you have got 100 data points, and also we already built our model. So our model is done. So once the model is done, what we'll be doing is, for each 100 data points, we will start with 1950. So if it's 1950, what happens to the sale price? We'll take an average, and then we'll move to 1951. For all the 100 data points, we set 1951 and see what happens to the overall sale price. Likewise, we do for all the individual values, and then we plot it. So once the sale price is, if you set all the data as 2000, the sale price is quite high. Also, there is I think it's here, partial dependence plot. There are a few libraries that supports really well. I will share this end of the session. You can also read this. Then we are trying to see the tree interpretation. For each prediction, why are we making that prediction? Like, what's going on inside the model? So that's a tree interpretation. I'll show you how to do that. For example, for 0th data point, the bias is 10.10, which means that's the average of all the data in this data set. For the average of this data set is 10.10, but our model says 10.01, which is quite low compared to the average. Why it's low is, that's explained by these numbers. Because for first data point, the year made is quite low. That's dropping the sale price to minus 0.3, but the product size is quite big, so that improves the sale price. And coupler system also improves the sale price. Then model ID also improves the sale price. Then sales ID dropping the sale price. Then tire size dropping the sale price, and other things also dropping the sale price. Overall, the net is minus 0.08 compared to the average. So here you can explain what's going on in each data point. This is quite powerful. Let's say in bank applications, let's say we are rejecting someone's loan application, and we can explain why we are rejecting the loan application. Maybe maybe he doesn't have house guarantee, something like that. So yeah, so that's quite powerful. So here Jeremy uses some deep learning, the same data set with the same pre-processing steps. You can directly apply deep learning based models, and you can see some of the predictions, and we can export the models. I think we pretty much covered most. Let's do a quick recap. So if you see lesson 6, we learned a lot about random forest and decision tree based models. If you see the pre-processing, most of the pre-processing are like filling missing values and filling categorical features, converting categorical features. Then for model, we learned about one OR model, which is one rule based. And also we can create many rules using decision tree. And we use Gini index to split. If the split is almost equal, means the Gini index should be like 0.5. And if most of the data in one group, means you will get very less Gini index. So less is better. Then for random forest model, we learned about quite a few hyperparameters, number of estimators, which is how many decision trees you want in the model, and max samples, how many data points we'll be using in the model, that's bagging. Then min sample sleeve, max features, and we'll also learn about out of bag score. Then for model interpretation, prediction confidence. So the prediction confidence can be found using standard deviations. Then we learned about feature importance. Then we learned about partial independence, and we learned to explain each individual row using tree interpretations. And one more problem here is extrapolation problem. For example, let's say this is in this data set, the maximum sale price is 10.8. So since we are creating lots of buckets, even for new car, we'll be saying 10.8. I think I'll show you the book. Yeah, let's go to the bottom. Yeah, this is extrapolation problem. So this is real, the blue lines are real data, but since our model didn't see the high numbers, for all the high values, we will always predict the same. So this is extrapolation problem. So I think that's why we will be using like neural network. So neural network model extrapolates very well, but decision trees and tree-based models, it won't, because it has not seen any high number in the training data. Cool. I think we are pretty much done. See you all next time. Thank you.